I don't want to be around anymore. I don't know.
So I went on vacation. Back home from vacation, let's get into it. One thing that was apparent when I was reading through the book, Chapter 7 didn't really have enough information that would warrant a whole video. So you guys get a double feature. And to kind of go through why I made that decision, Chapter 7 is talking about the way you can bundle your code into libraries or executable binaries and what that process kind of looks like syntactically. It also talks a little bit about public modules as opposed to other ones and how you can reference them, but functionally, it's information you need when you're actually building out a module, not necessarily something that is fun to go over. So I actually wrote out some notes, but I'm imagining what's actually going to happen here is whenever I actually set up a module, I'm just going to be going over the modules cheat sheet that exists in the book, because it seems like they actually thought, yeah, that's what this chapter's about. So I'm going to briefly go over my notes and talk through some small things in the book, but then we're going to go on to Chapter 8, which is the real big boy, and I think it's going to actually get us to the point where if I want to solve a problem, I can look to Rust as a go-to tool. Cool. So here are my notes. Very exciting. The actual way that they lay these out, and I figured a little picture might be useful, is you have our crates. We've been talking about these the entire time, and it's what we've been programming in. Whenever we opened up main RS, that was actually the root of a crate. And when we say cargo, new whatever, that was a crate. So we have these ideas of crates, and they hold these modules. What these modules mean, we can break down our code into little units that make them useful for some specific application. You can have multiple modules to a crate, and you can have multiple crates to a workspace. They said they'd get to that in, I believe, Chapter 10. Let me see. Nope, Chapter 14. So still a ways to go on understanding exactly how the workspaces benefit us. But we have two different types of crates. One binary, which is what we've been making thus far. And I did a little color coordinating here. So these lavender ones, main RS, and anything that would be inside of bin. I guess we can maybe do like a little whatever. Any of those two paths are going to contain binary modules for our crates. If we have something that we want to execute a program, the compiled binary with, it's a binary crate. Yay, who would have thought? And then the library crates are ones where it has code that we can use externally in other crates to perform some sort of task. So when we import some sort of thing like standard collections blah, or in the past we imported rand, that was a library crate. So we can also make those if we know that we're going to be producing something that we'll use elsewhere. This is largely not new information to people who have been programming for a while, but I wanted to make sure the distinction was super clear. So yeah, we have a path for the root path that defaults to main RS and libRS for the binary and library respectively, but we also have paths for binaries if we were to have something like a library that includes a binary inside of it. They also talked about, well, if you're going to include both, it's usually with the intention that you have the library, which is for distribution, but the binary is some sort of like, hey, you can call this, and here I'm using my own library for that purpose. So that's probably where we'd see this third case. To actually like invoke any one of these crates, we have this use kind of pathing. So we can be like use crate, garden, vegetables, whatever. So we'd have crate as the root, like literally the word crate, and then these double colon delimiters. Garden would be a module we create. Vegetables would be a module we create. It goes down the line until you actually have like a function or something you intend to call. And yeah, so that would be your absolute or root with this crate verbiage. But then you also have relative ones where you can say, I'm in a module and right next to me is another module. I can just call the name of that module without having to specify that from the root crate all the way down. So that's worth pointing out too. I guess I should probably also draw another module inside of another module, because that's kind of what's actually happening. I'll do that real quick. Yeah, you can have modules and modules, and that's kind of what these paths are separating. We also have this super, which is something that I'm familiar with. I've mentioned Python several times talking about these videos, but super is a way you can essentially refer to like a parent in an inheritance kind of way. And here they're just saying, like, if you are in a child module and you want to refer to the one above you, you can use super. So it's another way to have like a relative path. It does mention in the book that whether or not you use a root or a relative path is largely just whether or not you think there's going to be any sort of movement of these modules, and whether you'd move them as a group, in which case you could keep some relative or yada yada. But now you know that's how we can reference a module from another module inside of our crate. We also have a way to declare these modules. So it's literally just mod and then whatever the name of the module you want. And it's defined in a couple places. So the first one is just inside of whatever file. You say mod garden, and then you have your curly brace. You have your definition for whatever functions, whatever you want to include in that module inside of the curly brace. And there it is. But you can also say, if I have mod garden created somewhere in the project, I can include it in source and then whatever the module's name is, .rs. And so in here is where you'd say mod garden, curly brace, and then all that other stuff. And then lastly, they had this different version. They said it's old, it's still supported, but I guess they're trying to get people to move towards this kind of standard rather than having this mod.rs where you have an actual directory that's the name of the module and then something inside of that. I actually kind of like this better, just because, I don't know, having more and more paths is just annoying. And I'm the person who just CDs into a directory and then LSs every time. And well, I save a step, so cool. We also had generalized ways of importing stuff. So to the book, basically we can say like use, and then if we have two different things inside of, in this case, the std crate, we can go to compare and ordering and IO, or put it in like this. And we can also change the name of it by saying whatever this is from the use, and then saying as something else, as another name. And the example of renaming something with the as is on 135, where we have two different result modules, one's in standard format and the other's in standard IO. So since we want to use both of these in this project, we can rename one with this as, and as long as there's no conflicts there, everybody's happy. They also include something that I'm familiar with and not a huge fan of, which is the glob operator, and it's a asterisk here, and it just means import everything that's going to be inside this module. This is a thing that happened a lot in early Python in my experience, and it took a long time to get away from that. Fortunately, it looks like the book actually called out my exact use case for when you'd want to use the star operator, which is if you're writing tests. So it seems like there's been some lessons learned in the other languages that I've fiddled with. The real thing, though, that was like, all right, I'm not going to do this as just one chapter, is it brings out this little thing called a hash map. And hot damn, that's when shit gets real. So I use these all the time. If you don't use these, you need to use them. If you're unfamiliar with hash maps, or some languages call them dictionaries, some languages just call them hashes. They're not just hashes, but they're super ubiquitous, and you need to use these. So when they brought this out, I was like, cool. So now I can actually start fiddling with Rust. They've opened the doors. The Pandora's jar has been opened. And they know that had to have been the case, because they immediately start talking about these common collections, because yes, we're now at a point where we can talk about generics and why generics are cool and the value they add. Many books on algorithms talk about these collections as what I'm familiar with is just containers, and it's like containers hold stuff. That's what they do, and you'll see that there's functions to put and get things and sort things and all sorts of stuff like that. This is not the first time the book has actually talked about generics. In chapter 6, we actually use the option enum, and it has that T there. The T is the type that the enum needs to have the ability to encapsulate. We want to only make one data type, but have it work on a multitude of different inputs, things that encapsulates. So in this case, collections seem to be their way of talking about the generic data type that encapsulates other types. And so we learn the three most important, in my opinion, and we've also learned about all of them up to this point. So it gives us the vector, which is an array that is growing in some particular size. This is the generic form of whatever you've probably implemented in your algorithms class. Binary trees, linked lists, whatever. Strings, which are that, but specifically for characters, and some of the fun things you can get into in dealing with strings. And the hash map, which is like, again, the coolest thing that's ever existed. I'm just going to talk about them for a lot. This is just forewarning how much I like hash maps. So for our vectors, we see the first example is creating a, not generic, but a instantiated but yet uninitialized vector with i32 as the type for the generic. And we also have a macro further below, which allows us to kind of inline define a vector with some sort of stuff inside of it already. It does make a point here to say that the integer type is i32 because that's the default integer type. So if we're just putting these in and we don't specify like as whatever for every single thing inside of it, it's just going to go with whatever the default type is. The other thing that this is saying is that when we use this bracket syntax to access something inside of this vector, we need to make sure that the index we're providing it actually does refer to some sort of thing in that vector. Otherwise we have errors. And so in this case, we can say .get if we're unsure that the index we're going to be providing there is going to refer to something that's actually been instantiated or put into the vector. One thing we also see here is that we're using this asterisk as a way to dereference the mutable reference element in our for I in mutable reference of vector whatever. That's a hard sentence. I feel like the text here is pretty clear to understand, but it's one of the first times we've actually seen that dereference guy. And I'm wondering what the errors look like when you don't do this, because this is clear when you see it, but not clear to me that I would do it by default. One thing this brings up here is a way around a problem that I've been talking around, which is our generics have to be a specific type. So if we have this vector, our first one, we instantiate it with an unsigned 32-bit integer, and that's cool. But if I need to have multiple types, like I need a vector that can store a string and also store an int or whatever, I can't do that because the generic defines what type this needs to be when I initialize the vector. So how do we get around that? Well, we have enums. So whatever is getting put into it needs to be one of the following. Hey, that sounds like an enum. And then we can actually provide the values in the enum. And then when we instantiate our vector, we just say, hey, it's going to be containing these enums here. And that way it has one type, the type of this enum, but the enum can have multiple types inside of it. So we kind of work our way around this problem. And I don't know what other languages do under the hood if they allow their vectors or arrays to store multiple types. This feels a little strange to me. It feels kind of like a trick rather than something that's like intended. I also made a note here of this: a pop method removes and returns the last element on a vector. So hey, that sentence implies that we can make a stack really easy, and stacks are used also all the time in computer programming stuff. So also worth noting, super cool. There's obviously more to talk about, but I want to keep talking about different collections, and strings come up next. Boy, oh boy, it seems like everything that I do is basically string manipulation at the end of the day. So I'm glad that they gave a decent time chunk to what strings are and some of the problems you run into, because as mentioned before, strings contain UTF-8 characters. And UTF-8 is like a total mess because you don't guarantee that your character, whatever your character is in that string, is a uniform number of bytes. It extends for specific characters, and also like you can have glyphs that attach to other glyphs, and it becomes such a mess to actually understand exactly what you're looking at that when you're handling something like a string, which could be user input, it just becomes like this huge slog. It gives us some examples of methods that we're going to be using on strings, and for me, I'm gonna just have to memorize all these because they show up all the time in my life. But it says we have a plus operator, which is different in structure than a lot of the other methods we'll see regularly. For example, if I have two strings and I want to put them together and concatenate them, I can use the plus operator rather than having this particular string dot append or concatenate or whatever you'd expect that plus operator to do. What's weird is the definition of that. They say it has add. It uses self, and it actually takes ownership of itself. So it drops it, and it says that no, S1 has been moved here and can no longer be used. I said takes ownership, but moved. When we use the plus operator, it moves the first operand, the thing left of the plus. And I don't know if I like that. That feels weird to me, and I'm just going to keep that in my mind. It also mentions here that we have a format macro, and I use this in the past in one of my examples. When you need to create a new string of other strings, it seems like that's the default thing that I'm going to be using. You basically just get a string out, and you can treat it the same way we've been doing print line macros. You give it the curly braces and then give it whatever you want, and it's just kind of going to work. The chapter then immediately goes on to talking about how we access specific substrings inside of a string, and often I see this done with slices, and it gives us a good example why we don't want to do that. The aforementioned UTF-8 not having clear delimiters between characters or conjoined characters, etc., means that it's not particularly obvious if we want to get a string slice from sort of some index, how that would be useful. It even says, if you really need to use indices to create string slices, Russ asks you to be more specific using the square bracket and a range to create a string slice. And then immediately says, you probably don't want to do that. Here's some examples of things that you can use inside of strings that are probably going to get you what you want. So we have chars or chars, characters, which essentially just creates an enumerable that we can then grab any particular value from in a for loop. It also gives us this bytes function here, which creates an iterable, but over the bytes, the multi-part bytes that can represent each character. So yeah, the Cyrillic 3 and I don't know what that is, N, are represented here with bytes. And all these edge cases basically mean strings are complicated, and it says so much when it says, let's switch to something a little bit less complicated, hash maps. I'm not going to make them complicated. I want you to know exactly how these things work, because when I figured it out, I was like, that's genius. But first, we're going to talk about their just general use here. So if we just don't want to know what's actually happening under the hood, well, we can say that a map will map some particular key to some particular value. So in this case, we actually have blue and yellow, they're both strings, and then we have integers on the other end for the values. Storing things inside of a hash is done with this insert call, and then retrieving things is done with .get, and then we need to specify some other things. So copied says that we're getting an actual dereferenced value for whatever this option is, and the unwrapper 0 just means handle a default case if that doesn't exist, the key we provided. It's cool that they had these functions all next to each other, because this is kind of one of the default cases that I tend to see, but it's also weird because I'm used to the syntactic sugar of just having get, and then I can specify whatever key I want and then give a comma and then what I want the default to be in my default language and how I think pseudocode wise. So this feels a little bit verbose, but it makes sense because we're handling errors. It's also worth pointing out that we have a way to iterate through the key value pairs with referencing them and then giving a tuple for the key and the value, which then we can use inside of here. Cool, makes sense, like it, but the formatting for this actually just has a sentence here that says, whenever we use an iterator on a hash map, we get an arbitrary order for the elements. So it says, yeah, they're going to be returned in an arbitrary order. And that can be confusing if you don't know that that's default behavior, and it was like a huge thing. I'm going to stop saying Python. It's about Rust. I'm just saying, like, these are things that every time I see something like that, I'm like, oh, but what about? And then the book's like, well, let me tell you. It's just weird when I see a sentence after something that I'm like, oh, that can like kill you if you don't know it exists. And then it's like, well, if you didn't know that, you'd just probably gloss over and be like, okay, whatever. We also have a nice, here's how to put an item into a hash map if it doesn't exist, and otherwise just update it. So dot or insert, that's super cool, because when they give this example of like counting the number of unique words inside of a string, this is remarkably terse. And I think it makes a lot of sense. We also have a dereference here to count, because I guess when we say, hey, I actually want this entry word or insert, we're getting a reference back. So worth pointing out, it's not obvious to me that this was a reference just looking at this code, but I was like, oh, okay, I guess, I'll find that in like 2 seconds with a compiler warning. But worth noting, there's another dereference example. And my long-winded thing also, I noted when I was first reading it, it says, yeah, iterating over hash happens in an arbitrary order. And it says on page 155, but it's the top of 156. And it finally talks about the actual hash that's default use inside of Rust, which is SIP hash, and how that can prevent a denial of service by having a hashing algorithm that's specifically catered to that, which is a great way for me to transition into talking about what hash maps actually do and what they are. Hello there, Digital Me here. I wanted to take some time to talk about hash tables, but I think it behooves us to have a kind of review of Big O notation. Hopefully this is a review for everybody. There's plenty of examples online, which I know is a total hand wave, but I kind of want to reinforce some of these ideas, and maybe that provides some useful context as to why I think hash maps are so cool. So if you're unfamiliar, Big O is a notation that allows us to describe the efficiency of algorithms. And it's primarily concerned with how long something takes to execute based on how large the input is. So we can imagine a list and we can say, does it have 5 elements or does it have a Google of elements? And we can imagine that the algorithm needs to be much better depending upon how large the input is. So some basic things to consider here is that if we have a Big O that's like n factorial here, it's going to be just so bad. It doesn't matter if you have some constant time thing or some linear time thing, because essentially it will just dominate those other terms. So we only really consider this as the worst case scenario. And yes, there are other examples where we do want to consider the rest. But generally, we don't want to pick something that would be like Big O of n squared when we could pick something that's like O of n. All of this works really well in theory, but let's consider what happens in reality. So we have a list of n elements long, and we want to iterate over it. Well, depending upon the size of n, it takes n number of steps for it to be accomplished. So it would be Big O of n. And if we have an iteration over an array and then an iteration inside of that, so a for loop inside of a for loop, then we would say, well, for every instance of n in this first iteration, we iterate over n again. So it would be Big O of n squared, which is a non-ideal kind of algorithm. So let's look back at our list here, and I can say I want to change the 7th element of this list to be blah. And if I want to access that, I can simply point to the 7th element. And if I, let's say, reassign the 7th element to something else, it overwrites that value. This is all well and good, but it assumes that we know the index for whatever value we want. Accessing a value inside of a list is constant time. If I say I want the 10th element, I don't have to iterate over every single element to get it. However, if I don't know the actual index and I only know I want to access honk, well, I'd have to step through the 0th, 1st, 2nd, 3rd, 4th, etc., all the way until I get to that particular value. This is now O of n. So tied in with this, we have this idea that we need to know the index for it to be efficient. And we can imagine that there's a use where we don't necessarily just want to use that integer that specifies the index. We'd like to use something else. In this example, I just use a string. So if I say I want the dog element of list, I want woof as an output. Or if I want the goose element of list, I want the output honk. Well, that's fine, but we're not really talking about a list anymore. We're almost talking about a map. So how is this actually implemented? Well, we have a hash, and a hash function is something that takes an input and produces an output. Usually we see it as hex, and it's important to note a standard number of things for hashes. One is that they're fast, so we want them to be as efficient as possible because they're so ubiquitously used. 2 is that they're deterministic, so I give it the same input multiple times, I will get the same output multiple times. But I also want to make sure that they're unpredictable. 3 is that if I have only the output, I can't know what input gave that output. This is called a one-way function generally. Cryptographers call that feature pre-image resistance, but it's also important to note that there are some very important differences between cryptographic hash functions and non-cryptographic ones. And 4 is that their output needs to be uniformly distributed against the entire output space. Imagine you have an absolutely terrible hash function, but it has a byte of output space. It can return anything from 0 to 255. A terrible function would produce some of these values in that output space more regularly, versus one that would be good and uniformly distribute the output. How they're used in a hash map is that we take whatever input we wanted here, let's say dog, we push it through the hash function and we get our hash. We then can take that hash and modulo it to the length of the list so that we now get an integer which specifies the index that we want to put this value at. I'm going to place it in our fake list as a tuple with the key and value for a very specific reason. But for now, just imagine that if our hash function's good and if our list can arbitrarily grow and shrink, then it's very unlikely that we would actually have two of these same keys point to the same index. So if we wanted to access any particular value in this hash map, we could say, hey, I want to get the dog element of this. And cool, we take that input, we put it through our hash, we take that hash, we mod it by the length of the list, and now we know where to start looking. I now see that I have an element in here that's dog, and cool, I return woof. Pretty cool. So let's say we actually do this with Goose and we get the hash, we mod it, and we get 0 back as our index value. I'm going to call this a bucket, and this would mean that we have to put the Goose inside of the same bucket as dog. Well, we can fix that by saying that our generic list will contain lists themselves of these little tuples of key and value. And then if we needed to access Goose, we might still get that 0, but accessing it, we know that we only have to see dog's not what we accessed, and now Goose is. So in the case where we have a collision on one of these buckets, it's still not approaching n. So if we think back about our big O notation, it's actually almost constant time, and in worst case scenario, we have only collisions for those buckets. We're now approaching big O of n. Hey guys, what's up? Another day, new digital me here. But yeah, I woke up and my throat is bad. It's not doing well. And I'm going to hopefully record this as quickly as possible so you don't hear my voice just slowly fade away into nothing. For chapter 7 and 8, what I actually did was I made different modules. I made a storefront and the back. So let's actually look inside of our main. And you'll see that what I did was I defined both of these modules with the whole just regular semicolon and put them in different files. Whereas this payment gateway, I actually did it inline. So we have 3 modules here. And then I guess you could also say we have our root module here where we actually have main. So let's talk through some of the stuff that I learned. Exciting. So the first thing you might notice is that we have some more little, I don't want to say decorators, macros that we're putting on top of our struct and enum here. And mainly, I just had to Google these because, man, this did not look nice highlighted for everything that was unused. And the debug one, I like printing stuff out. So the only one that should be exciting or new or be like, what does this actually do, is this derived clone. What I found was if I had a reference to something and then I wanted to dereference it, the easiest thing for me to do would be to clone it. And unless the struct actually derived clone, I wouldn't be able to do that. The example that I use that is in the back module. What I wanted to do here was say, hey, when I actually match this inventory item, I want to return that so that you can compare and whatever you actually needed to do with that. And unfortunately, I tried to do this with the .clone, and when I initially didn't derive clone here, it exploded. So I'll save this real quick, and you'll see that we'll get an error here that says the trait condition, beep boop, the trait condition is not satisfied. The trait clone is not implemented by condition. So once I actually added in this clone macro, it worked. There's a little subtle thing there too, which is the product was clonable, but not every attribute inside of it was clonable. And so that also means that now the product is no longer clonable because it just doesn't know how to make a new instance of whatever attribute is not inheriting the clone trait, copy trait. Let's look at that one more time. The clone trait. Okay, cool. Yeah. So the copy trait was more for, if I recall correctly, things that can exist on the stack, and the clone is for things that were on the heap. Cool. If I'm wrong there, that's perfectly fine. Another fun thing here was when I actually created some of these functions, I didn't have the correct ordering of the reference, the mutable, and the name, all that. So here are the ones that I tried using, and hopefully I don't seem silly in the future for writing them out the way I did. But in this case, I said, hey, for this module payment gateway, let's make a function called purchase. Why not? And if I want to talk about this balance here, right, like I want to remove something from the balance but still give it back to the person after the function's done executing, I knew that I'd have to have a mutable reference, right? So check it out. I say, hey, let's make a mutable reference to balance. And when I ran this, it says, hey, you have a mismatch type. I expected a float 32, but I found what looks like a reference to a mutable variable that we don't intend to use. So that wasn't super obvious to me. Let's actually look at the full error here, because I feel like that might actually be more clear than just a single line. Okay, so we do have the same error here, but actually right below it, it says to take a parameter balance by reference, move the ampersand mute to the type rather than this name. So cool, that makes sense. The second one that I tried was, I was like, oh, okay, well, I need balance to be mutable, but I need the reference over here, which again was broken, but in a different way. So this time it's saying, hey, you don't need balance to be mutable. And I'm like, what do you mean? I'm dereferencing it and I'm mutating it. And then down here it says, well, I can't assign to balance because it's behind a reference. And so this one was a little bit more confusing to me. So let's see what the error says here. Does it give me a hint? Consider changing this to be a mutable reference. Okay, so we get the ampersand mutable F32, which is what I ended up doing. But yeah, I guess in my head, I still think about putting the ampersand mute in front of the name rather than the type. So that won't happen again in the future. Hopefully. It seems to work just fine now. Oh, and silly me. Okay, so and silly me, I didn't talk about this. So I have these two files open. I didn't even tell you where they were. So inside of source, we have our main file, and then we have storefront and the back, and those correlate to our modules that we define. We have mod the back and mod storefront, and those go in storefront and the back there. So we have an example of one being inlined, and then we have the other ones that are their own files. Cool. The only other thing that I'd want to say for this main file is that I am not a super huge fan of the way that I have to call expect the way that I do. It's me just being lazy, but I actually watched a Tauntaun video and he was like, the question mark operator is really cool.
You might notice we are using a question mark operator here, and it's because the build function can fail. If the build function fails, we'll crash the program gracefully. That's what the question mark does.
And I was like, the question mark operator is really cool. And it says, hey, you can't use this because you need to be in a function that returns an option, and main doesn't return an option. It doesn't return anything. And I'm like, well, that's stupid. I don't like that. I will say that the error there is not super helpful at first reading, because at first blush I thought it was like, I can't use this because it returns this. No, it doesn't return like this unit tuple. It returns an option, and it's because it's referring to the function that this is being called in. So now I'm in the back module. We're using our hash map, so super cool. There are a couple small feelings that I wanted to get across here that I'm not certain they actually really make sense. So I'll try to explain it. Basically, I wanted to have this data exist so that I could call it inside of the function. And, well, the way that I thought about it was I have a couple options, but my default strategy is I should just use something like SQLite. But I'm not jumping into libraries yet, and I feel like that's pretty outside of our babies first. So it's like I should just define something inline. And what I initially wanted to do was just have this inventory exist in the base of the module. So if I take this and I paste and I pull it in, boop, boop. What we get here is you can't use let. I know now that this is related to ownership because like the module doesn't know about this. It doesn't belong. There's no scope here that it belongs to. And I know that there are ways to define things as globals, but in my head, I was like, do I want to use a global for this? Like I could, but And when I passed it by my friend Stu, he was like, actually, I think that this makes a decent amount of sense because it means that testing stuff like this is a lot easier, which is a very good point. But it was the first spot where I was like, oh, actually, I'm failing on like the structure of this, not even just like, how do I write the code? So it's a little bit weird, but I think I got past it. Basically, I just have this initialize guy and it returns the actual hash map itself. And so when I actually call initialize inventory in main, that means that main now is in charge of the inventory. It now owns it. So whenever I want to use it, I can like pass the reference to other functions and we're happy. It does mean that every single time that I want to look at something inside of the inventory, I actually have to have this hashmap string product, which I'm not as much of a fan. I'm not a fan of these very, very long function definitions. So that it's fine. I'm just being a little baby. Other fun things here is I actually made this big borrow and big ownership because I was having a bit of a hard time with actually referencing the name here, or I should say the name inside the attribute that I wanted to match in this product. So when I initially created this, I had essentially taken ownership of the attribute name inside of our product. So I can show what that looks like by creating this function and running it and having it be syntactically correct. And what we see is it's like, hey, I can't move p name out of a shared reference, which illuminated a problem in my head. I assumed that if I had a reference to this product, right, like I'm iterating over a hash map that's a reference, well then I'm assuming that p is going to be a reference, and then the key would also be a reference. And so what happens is it goes, no, you're not allowed to do that. And the error it gives is pname has a type string. The borrow here actually I included for a different reason. So I was like, okay, well, I can't take ownership. I'm just going to use a reference. And if I comment this out, we're actually okay. And I was a little bit confused when I wrote this out because, well, this big borrow here is actually taking a reference, a string slice. That's the word it's looking for. And so it will return whatever the parameter is here. And so we're happy. And so I say pname, and then I make that a reference. We should be happy, right? Not in my head. So pname is a string, like capital STIRNG string. And I asked for a string slice. So I thought I'd get a type error, which is, again, why I'm like, okay, well, I guess I can use a string slice. So yeah, it's a little strange when it works, and I don't know why. I only realized that I thought I was making a type error issue after I wrote it. But if we jump back here, if I change takes ownership to a string slice, which again, now that's a string slice, it's a reference, right? But if we say, let's change this to just a regular string, and then we say take ownership of this p name, we will get a type issue. It'll say, bro, I can't take string and, well, it actually doesn't even say that. It says the size of string can't be known at compile time. I guess I assume that this would just be, okay, no, right above it. Read with understanding. Shiddy, come on. Expected string found struct string. So I guess it makes sense. But this is me fighting basic typing thrashing around like I would. This is also a really good time for me to bring up my friend Stu again. He helped me out by saying, hey, look, if you're not going to be a sane and rational person and use an actual big boy IDE, you're going to have these kind of problems where normally it would just tell you the type it's thinking about, and so you know what you're looking at. And I'm like, yeah, fine. So he told me that before this tool existed, he used something like this. So it's a cute little trick. If I didn't know the type of P, well, I can say let a variable I don't care about be the type unit tuple. I think it's just, they just called it a unit struct, but yeah, anyway, equals that value, right? And so if I save this, it'll say, that's wrong. That obviously doesn't work. P is not that. I can't assign that. We have a type error. So mismatched types, expected this but found a reference to product. And I'm like, oh, okay. So now I know, in this case, when I'm iterating over that hash map, P is a reference to product. Got it. Okay, we're not going to fight the bar checker. I'm comfortable with the fact that this works, and I will learn in the near future. Also, shout out to Love Belinas. Hopefully I said that right. Saying, hey, you should use Rust Analyzer too. So I'm gonna get that working after this. Another fun thing about this lookup by name, right? This is not the function I wanted to write. Okay, it's what I got. The lookup by name here would be infinitely better if I, instead of actually having to pass out this product like this, if I could give it a reference, right? Because I can say, hey, you only need to know that this thing exists. You don't need to modify it. You don't need to make your own copy of it for some reason. You just you want the information that is actually in there. Cool. Well, you can't do that. Why not? Well, when we actually defined the inventory, and it contains these products, right? We are now saying at the time this is created, beep boop, hey, inventory is owned by this function, right? And all the things inside of this are also owned by this function, right? Because if this goes away, we have a problem. Makes sense. Everybody's happy. We return this, and then now it belongs to main. So down here, main is now the owner of inventory. It's been moved. Cool. If at some point somewhere else I give it a reference to one of the objects inside of this hash map, then I have to know inside of this main function to not drop this, to keep it alive, which, main's not a great example here, but it means that the compiler now doesn't know explicitly what needs to own what where. Like, okay, if I do want to drop this hash map, is that okay? Like, should I still have the reference to the product somewhere? So it actually says this in the error here. There's a missing lifetime specifier. We actually don't know how to tell the compiler, this is actually okay. We want this behavior. So what I ended up doing was I just said, we're not going to read ahead in the book. I'm not going to cheat myself and you. And instead I can just say, hey, I can just return this product if I clone it. And that's where we got our macros up here for derive clone on both the product and the condition. The last module in this crate was the storefront. I had a couple things that I wanted to talk about, but I'm worried that I'm not going to do a great job of explaining them. I wanted to make a different area to call purchase. One, so that I can do the rename guy here, but two, I like the idea of having the balance exist somewhere else, and then I had to pass that down as references and then modify it and then get that reference back and compare it, so that I could say that I understood the scopes better. That was not super obvious to me. So the first thing was this mutable reference thing, the way that it's set up here, is correct in the same way that the other one before needed to be corrected. But I assumed that if I wanted to take this reference here and then change it in some capacity, right? Like I wanted to remove the item quantity on line 17. I figured I could just say this is the way the book describes accessing particular elements inside of our key store, right? So I have a mutable reference to the hash map. I wanted to get an item out of it. I can't actually do this. Again, I thought the thing inside of the hash map would kind of have the same, reference and mutability specifiers as its parent, and it doesn't. So when we actually tried to change this here, it says, hey, I can't actually assign to the item quality. If we use our little trick again, it says, hey, we have a reference to product and we don't have a mutable reference to product. I, presumably passed this mutable hash map here for a reason. Turns out that the compiler didn't give me a great answer as to why this is happening. So it says, hey, it's behind a reference. You should make it a mutable reference. What I ended up doing was I looked in the hash map documentation, and there was a function called getMute, which works the same way as get, but we get a mutable reference back. So yeah, if I do this, and it says, now we have an option, which is a mutable reference. So we have a mutable reference to a product, and now we can, change it. So going back, so we have get mute, expect, and now item is a mutable reference. We can then modify that. I will say this is a little unclear to me why I don't dereference it, right? So I guess the reason is because this item quantity is something that actually derives the copy trait because it is small, but that might need to be dereferenced in the future if it's something that's not that. Like, for example, if I had that enum there, maybe that would be a little bit different. Okay, let's find out what happens. What do we get? Condition can't be dereferenced. What? Why? But does it work? It just works? Okay, how do I modify a value inside of this? Oh no. Oh god. Wait, that was what I had before. But this is creating a new guy. It's not modifying it. Okay. Can I make something quick? You're gonna be mad if I try to use test. My understanding of how we need to implement the dereference operator needs to be stronger, and that will come in time. For now, I'll let you know that the get mute got me out of a bind here, and that I am okay just accepting that I will have to learn more about how those actually all fit together. I guess the last thing I really want to show is that this all kind of worked, which is surprising given my gross negligence and inability to understand how a lot of these pieces fit together. So thank you, compiler warnings. They basically told me what I needed to know if I read with understanding. Yeah, let's walk through what this does. I made this inventory. We talked about how that actually needed to exist inside of a function and then get moved in here. So inventory is now owned by main. I also made a balance here, and I made this mutable so I could pass it down via a reference, change it, and then see if that actually did change. I did a quick check to check if something was in stock. So this is a way to iterate over a hash that's not going to just be looking at the keys. I figured that'd be a useful way to kind of like reinforce the big O of n if I don't set these up correctly. But I'm also accessing them by the SKU later being right here, where I take that in stock, I access the SKU of it, I make it a reference, and I pass that to purchase. I also pass in my balance, and boy, oh boy, I can check my balance after I purchase it, and it should go down. You saw nothing. We access a different type of product here just to see if it works, and print that. So yeah, when I run this, it works. So yeah, we see what is available. We have our sock and boppers by the lookup, and it says it's in stock. And we buy something, it removes it from our total, and then yeah, we check another thing and it exists. So I feel like, it took me a while to kind of get around some of the borrow checkers idiosyncrasies. I think it makes sense if I think about it, but the way that I invoke something and say I want this to be mutable isn't obvious to me yet, so that'll come in time. So yeah, exciting and fun chapter. I'm not going to go back to my desk because there is snot everywhere. But thanks for watching this far if you got here. As always, if you have interesting things to say or are willing to give me input, please let me know in the comments. I'm very thankful for everybody who gives me input. I'm sick, so I'm gonna go now. I'm gonna go take a nap.
I'm taking a nap.
You want to take a nap?
I'm taking a nap here.
Okay, take a nap right there then. Good night.
Good night.